Alrighty, in notes number 4, folks have been working on the Lewis structures, and we've added the shapes idea onto each of the 4 Lewis structures. Now, what you see here, great success today with the trigonal pyramidal, the tetrahedral, and then in the lower right, the PF3 is also trigonal pyramidal. What I want to do is I want to talk a little bit about CO2 and relive the moment when people are making their Lewis structures. If we do this, we say carbon brings 4, and each oxygen brings 6. That's 12 plus 4, that would be 16 electrons. That's 8 dashes to you and me. 8 dashes. Now, as I look at this, I think let's put carbon in the middle, oxygen, oxygen, and I'm going to just 1, 2, 3, 4, 5, 6, 7, 8. We wall off the perimeter. But then here's what I notice. Carbon only has a total of 4 right now, so that's not going to be my final answer. I've already used my 8 dashes, and so this is what most folks have done. They then said, well, let's make a double bond. Well, that still only gives the central carbon 6 electrons. And so what students have done, they then said, well, let me take one from this side and add that. Now, each of the 3 different atoms, the oxygen, the carbon, and the oxygen, they all now have an octet, and that would be considered a Lewis structure for CO2. Reminder on the back of notes number 3, the 4th bullet down, I believe it is, it talks about multiple bonds, double or triple bonds, count as one bonding pair. So I see that as a 2 bonding, 0 non-bonding, and that's going to be linear in its shape. Okay? Linear in its shape. I want to talk about another possible Lewis structure for CO2. For CO2, I want to relive the moment here where I look at this and I say, I have 8 to spend, 1, 2, 3, 4, 5, 6, 7, 8. And let's make the oxygen on the left extra generous. Bing, bing.
What?
Please copy this down as another Lewis structure that is possible. Did you have that? Okay. First one all day. Congratulations. This is a full credit, and it would also be linear because it's a triple bond, counts as one bonding pair, much like the single bond. So it'd be a 2, 0. That would be linear as well. So I could do a triple bond coming from the right side too. Now, it turns out one of these Lewis structures, one of the 2 Lewis structures is officially right. If you're like, but wait a minute, they each have an octet. On paper, they both look reasonable, but only one of them matches what we observe in nature. Lewis structures are only as good as their ability to predict what nature does. Nature only does one of the 2 Lewis structures. And it turns out it's the top one. But in case you're like, yeah, it kind of looks balanced, evenly distributed, I like the flow. No, take all of that out, because if we flip the page, boom! Here's the right way of looking at it. The key question is written here in bold. If you've got more than one, which one is correct? And by correct, I would say is observed in nature. By observed in nature, that's what we're after. We can't see it with our eyes, but can we can we learn what the answers in nature are and create rules that allow us to predict? Yeah.
So if they made like synthetic triple single on carbon dioxide,
It's unstable, and so it'll revert to the lower energy form. Okay. So here are the two rules. Now, the formal charges, we want those to be as close to zero as possible. Now, the formal charges were introduced, the idea was introduced in notes number 1, but it's been a while, so we're going to revisit that. Secondly, if you do have to have negative charges, please make sure it's on the more electronegative atoms. Reminder about electronegativity. We said in notes number 1, fluorine is the king of electronegativity, meaning fluorine and things that are closest physically on the periodic table to fluorine have the highest electronegativity. So I look at something like carbon and oxygen, and I say oxygen is right next door to fluorine, so I would predict that oxygen's electronegativity is going to be higher than carbon's. Because again, it's farther away, carbon is farther away from fluorine. Nicholas? Take them out for right now. I don't want to confuse us. Here's what I want to do for example number 1. I want our notes to all look the same. So I want to split the page in half, or split that region in half. And I'm going to put a phosphorus in the middle, an oxygen up north, and then the chlorines would be east, south, and west. I'm going to copy that same pattern over here on the right. Phosphorus in the middle, oxygen up north, chlorine, chlorine, and chlorine. Now let's connect things, and on the left we're going to do single bonds coming off the phosphorus. We're going to wall off the perimeter. Okay. On the right, we're going to do single bonds to the chlorines. Single, single, single. Let's go ahead and wall off the chlorines. Now for phosphorus to oxygen, I want to make that a double bond. And on that oxygen, I want 2 dashes. 1, 2. Okay. And then you're like, but wait, that breaks the octet rule for phosphorus. I look where phosphorus is. It is after silicon, and so it can go past the limit of 8 electrons. It has the capacity to go beyond 8. It's after silicon, number 14. Okay? Now, the formal charges. Formal charges, it's been a while, so I want to make sure that we're good with that. The formal charge, and let's calculate for the one here on the left, the structure on the left, let's talk about phosphorus. Phosphorus is in group 5A, so it should have 5 electrons assigned to it. But when I look at this chart, at this Lewis structure here, 1, 2, 3, 4. 5 minus 4 is equal to a positive 1. I'm going to go ahead and put plus 1 right there next to the phosphorus. I'm going to switch and go green here for the chlorine. Chlorine is in group 7A, so it should have 7. I'm going to use the one down south here. 1, 2, 3, 4, 5, 6, 7. Now this chlorine is single bonded and it has a formal charge of 0. The chlorine on the left would also have a formal charge of 0, and the chlorine on the right would have a formal charge of 0. As I look at this, I am now thinking one of the big ideas we mentioned in notes 1 is that the sum total of all the formal charges must equal the observed charge on the substance. This is a neutral compound, so I'm counting on this oxygen here up north being -1 to cancel out the +1 formal charge. Let's see what we've got. Oxygen is in group 6A, so it should have 6. It has 1, 2, 3, 4, 5, 6, 7. 6 minus 7, -1. I'm going to highlight this and see where we are. +1 and a -1. I look at that and I say, that's not bad, because I want to minimize my formal charges, so if they can't be 0, at least they're +1, -1. I then look and I say, well, comparing where phosphorus and oxygen happen to be on the periodic table, I would want a negative charge to be on the oxygen, not phosphorus. So this is not bad. +1, -1 adds up to 0. The positive charge should be on phosphorus, not on oxygen. Let's take a look at the one on the right. In the interest of time, the chlorines have not changed. So I'm going to put a 0. I'm going to put a 0. And I'm going to put a 0. Now let's take a look at the phosphorus. Phosphorus is in group 5A. It's supposed to have 5 minus 1, 2, 3, 4, 5. Phosphorus has 0 for its formal charge. Let's look at the oxygen. Oxygen should have 6. It has 1, 2, 3, 4, 5, 6. We have a winner because 0, 0, 0, 0, 0. The one on the right is the better Lewis structure. Nature does what we have on the right. That's in contrast to what we would have you believe based on the first year course, where you say the octet is everything. But nature doesn't care about what we think. It does what it does. And the rule of the game would be minimize the formal charge. So which one is the preferred one? The one on the right, because all formal charges are 0. That's the critical way of looking at it. Okay? Not difficult, we just got to learn the rules of the game, so to speak. Let's take a look at the next example. There are 3, so I'm going to, again, I want your notes to match mine, so it's easy for everybody. Hopefully that's about 1/3, 1/3, 1/3. And I'm going to write it in the order that it's listed, NCO, in a straight line. So it's NCO, NCO, and NCO. On the far left, I'm going to refer to that as the triple single. Bing, 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 bing. Wall off the oxygen. Then put 1 pair on top of the nitrogen. In the middle, I'm going to call that the double-double. I've got the 2 lone pairs on the nitrogen and 2 lone pairs on the oxygen. On the far right, I'm going to call that the single triple. Wall off the nitrogen and 1 extra on the oxygen. Now what I need to do is I need to calculate the formal charges. And I'm going to do it really kind of mechanically here of NCO, NCO, NCO. Nitrogen, according to the periodic table, should have 5. Carbon should have 4, and oxygen should have 6. 5 minus 4 minus 6 minus 5 minus 4 minus 6 minus. As I look at that, there's the first one. Again, assign formal charges for everything. Abby, which one just seems horrible? Why? Yes. Hopefully, you despise the third one as much as I do. Furthermore, if you're like, well, what do you got against -2? I mean, well, and also, let's make sure we see this. Hey, Bracken, I thought you wanted all the formal charges to be 0. Yes, but remember, this is an ion with a charge of -1. So you cannot have everything be 0. Something's wrong there. But the world is not spinning right if oxygen has a +1 charge. Oxygen is right next door to fluorine. It has a very high electronegativity. So if anything is going to be negative, it's not going to be nitrogen, it should be the oxygen. And the fact that this is a -2 is just that's just terrible. That's just terrible, okay? We want to minimize the formal charges. +1, -1, that's not bad. This -2 stuff, no. So then we ask ourselves, let's go with Eric on this. Eric, the first one or the second one? Where should the -1 go?
First one.
Why?
Because oxygen is more electronegative than nitrogen.
Absolutely. So this is the best one. Be careful here because a lot of times students will do this. This is the wrong way of thinking about it. Hey, I know a little something about electronegativity. Yeah, oxygen's going to want a lot of electrons around it. So I'm going to put the triple bond next to the, no. I love the middle one. It's kind of balanced. Reminds me of CO2. Best one, right here. Minimize the formal charge. How do we write this? Here's the A+ answer right here. The one on the left is the best because it minimizes the formal charges and has the -1 formal charge on the more electronegative oxygen. You do that, that's called a 5 on the AP exam. That is a please bring the A game type of response. Okay? Questions about this? Please take a moment, flip the page if you could. I don't like how I've written this, so I want to clarify. For CH2O, you could write it this way or you could write it that way. Okay, now I've highlighted to help you see where I switched the oxygen and the carbon. Everything has an octet, okay? But please tell me which of these two would you expect to see in nature? Similarly, boron trifluoride. You'll see the way we've been writing it here. Then this one I would describe as you're going to get an octet and you're going to like it situation here. Please tell me which is the better one for BF3. Okay, please take a moment and do that if you could, please. Crank them out. Not difficult. it's all about the formal charge. Alrighty. And please take a moment and look up at the board when you get a chance. Again, our goal is to minimize formal charges. And the one that I think is most interesting is on the far right, where we say, but why in the world would boron not want an octet? To achieve an octet in this, you get a -1 formal charge on boron, and oh my good, this just doesn't even seem right. I'm emotionally fragile when I see fluorine with a +1 formal charge. There's just, so this is just, the idea of creating an octet is like water going uphill. It just is not, no, that is not going to happen. So the ones that are boxed, once again, just hitting it pretty hard here, these are all 0 with formal charges. Okay? And again, that's the lens through which we look at these to say, what is nature going to do? We created the rules so that we would always get the right answer in terms of what nature does. All right? That's how we want to think about it. All right? Now, Eric, question?
So is electronegativity stronger than the octet rule? Like, does it override the octet rule when the octet rule has to break the electronegativity trend?
There is a certain stability associated with octets. But the pain and discomfort of putting a +1 on a fluorine outweighs any benefit that we would see of the octet. So it's kind of a case-by-case basis where we say, if this is what we observe in nature, why would it do that? Oh, okay, it must be that this would require too much energy. And you're not going to get the stability that you thought you would get. Okay? Now, I went around, and in the interest of time, I want to go on, but what you are able to do right now, not at the moment, because I want to finish these notes, but problems 4 and 5 are just like what we've been doing in terms of formal charges to pick out the best Lewis structure. What I want to do is continue on with the notes and crank these out, okay? Because this is a little bit surprising here. Not beyond us, just kind of surprising. 3 times 6 would be 18 electrons, or 9 dashes. And watch how I do this, okay? Because this is going to be a little bit strange. 9 dashes, link them together, 2, 3, 4, 5, 6, 7, 8, and dump 1 on the central atom. But I'm not done, because I've starved my central oxygen. So for me, I'm going to erase the dash on the left. I'm going to make a double bond. Well, somebody else might have said, well, my oxygen on the right was the generous one. So for me, it looks like this. Not a problem. Well, here's what I want you to envision. Science is awesome when the power of prediction holds true. We feel smart. We do. We knew it was going to work and it did. On the basis of the Lewis structures, and I've got the table here, I would predict one short O to O double bond. And you see down here, the bond length is listed as 121 picometers. And I would predict one longer, and I'll draw it a little bit longer, O to O single bond at 148 picometers. We get the new instrument. We send you in to run the analysis of the bond lengths of ozone. You come back, and I say, oh, good. One long, one short, right? No, it didn't. Okay. Well, which kind of bond was it? A single bond or a double bond? I don't know. Well, was it 121 or 148? They were both the same length. Which length was it? 128 picometers. Something must be wrong. Because it's not a true single bond, it's not a true double bond. You can see mathematically it's not perfect, but those are the real numbers. It's wedged somewhere between a single bond and a double bond. In reality, what we observe when we look at ozone is that both bonds are equal in length and strength. And they are 128 picometers. It is almost as if oxygen, oxygen, oxygen. Here we go. Time to get weird. Boom, boom. Those are not electrons. It's almost like what we've done is I took half of this bond and I said half stay here, half are going over there. It's not a single bond. It's not a double bond. It's a 1.5 bond. And if you're like, that doesn't exist, tell that to ozone. It really doesn't care what we think should be. We have two equal 1.5 bonds. Now, bond order we've not talked about, but I think you're going to be able to crack the code. A single bond has a bond order of 1. A double bond has a bond order of 2. A triple bond has a bond order of 3. So, Allison, what should the bond order be here? 1.5, absolutely. It's a 1.5 bond, so the bond order is 1.5 or 1.5. That was so much fun. Let's take a look. Resonance structures, we'll talk more about that. Let's divide this into 3 columns. Bing, bing. And watch how I do this. We're going to go carbon in the middle, oxygen, oxygen, oxygen. Carbon in the middle, oxygen, oxygen, oxygen. Carbon in the middle, oxygen, oxygen, oxygen. For clarity, I'm going to go double bond there, double bond there, double bond there. Single, 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 single. Let's wall off the single bonds. The oxygen that is part of the double bond only has 2 dashes like that. Once again, you would rightfully predict one short C double bond O with the bond length of 121 picometers. You would predict 2 longer CO bonds. It would be 143 picometers. In reality, all three bonds are equal in length and equal in strength. And what is the length? What in the heavens to Betsy Lou? It's 130, which is somewhere between a single bond and a double bond. So all three bonds are equal in length and strength. Now, Olivia, bond order. Let me give you the visual here. You can have one, you can have one, you can have one. What's the bond order? 1.5. See, I had this bond here, and I said, you can have some, you can have some, you can have some. What's that bond order? 1 and 1/3. Yes, I've got 3 oxygens to share a bond. Now, here's where it gets really weird. Really weird. Well, I thought a dash represented 2 electrons, Bracken. How did you, yeah. Nature doesn't care. So it's like, how do you, 2 electrons over 3? Yes, it's a 1 and 1/3 bond. Because nature does what nature does, and it doesn't care about us going, but you got to make up your mind. I'm going to be you. 3 bonds, all identical. Okay? And that is really, really difficult.